So, we're talking about binomial distribution. And so when we talk about binomial distribution, we're talking about binomial experiments. And in order to be a binomial experiment, we have these 4 requirements that have to be met, and you need to check them every time to make sure that it is in fact a binomial experiment. Because if it's not, the stuff that we're going to be working on doesn't really apply. Okay? So, first requirement. Each trial of the experiment will only have 2 outcomes, and we're going to qualify them as either successes or failures. Okay? And for example, they have to only have 2 outcomes. So like when we flip a coin, we talk about that, there's only 2 outcomes. You can get heads, you can get tails. That's it. Okay? So that's the key thing, binomial. By 2. So that's the first part. So if a particular trial has more than 2 possible outcomes, it is not a binomial experiment. The second part, there must be a fixed number of trials. So you have to know from the beginning, like, we're going to have 15 trials. Or whatever the set number is, it has to be set. It's predetermined. Next part. The outcomes of each trial must be independent of each other. So what happens in trial 3 can't impact the probability of trial 7. Okay. So the outcomes must be independent of each other. And lastly, the probability of success must remain the same for each trial. So 3 and 4 are kind of related. In order to be independent of each other, the outcome is not affected, which means the probabilities will have to stay the same for each trial. The probabilities for trial 1 will remain the same for the probabilities of trial 100. Okay. They aren't affected as you move along. So what we're going to do on this screen is determine if these experiments are binomial or not. So if you want to take a picture of that, that's fine. If you want to write them down, that's fine. But all we're trying to do is see if it meets the 4 criteria. And if it does, then it's a binomial experiment. If it does not, then it is not. So write those down, get those down, and then try to decide which ones are binomial and which ones are not binomial. 1/3 of households in the U.S. have a computer. 200 households are randomly selected. A count is made of the number with the computer. So, first off, are there 2 possible outcomes here?
Yes.
What are the outcomes? Have a computer or not have a computer. In this case, which one is the success? Having a computer, okay? So we've got that part. Are there a fixed number of trials? We're counting exactly how many households? 200. 200, so we know that already. The probabilities are independent of each other. Is the probability of somebody having a computer impacting somebody else's household about whether or not they have a computer? What is the probability that somebody has a computer?
1/3.
1/3, okay. Does it change as we move along? No, it's just 1/3. Okay, so it meets all the criteria. All right, so this we would say is a binomial experiment. Okay. How many had that? Good. All right, second one. 2 outcomes. What are my outcomes for B? Can I have them? Red or black. So it satisfies that one. Are there a fixed number of trials?
Yes.
What's that? 5. Okay, we're going to draw 5 cards out. Are the outcomes independent of each other? One of those.
Yeah, no, they're not.
Why are they not?
There's no replacement.
Without replacement. So if it said with replacement, we put the cards back every time, then each trial wouldn't be affected by the previous trial. But because once we pull a card out, now my probabilities change, because instead of having 52 cards, I have 51 cards or 50 cards or whatever. So this is not binomial. Okay? How many had that right? How about the last one? 2 possible outcomes are what? What's our success? What are we trying to get here? A 5 or a not 5, right. So there's my 2 outcomes. Are there a fixed number of trials?
No,
Why not?
it's until 5.
Because you just keep rolling until you get a 5. We don't know how many there's going to be. So right off the bat, we're like, nope, not binomial. How many had all 3 of those right? Good. Okay, that's the part. Second part, we got to get into some numbers. Okay, binomial distribution, the outcomes of a binomial experiment and the corresponding probabilities of these outcomes. So now we're going to start looking at some of the math related to binomial experiments, and that's when we start talking about binomial distributions. And there's a formula that we're going to go through and that you're going to need to know, and you're going to have to know all these different parts and what they mean. So here's the formula, okay? And we'll talk through what it is. All right. This is the how to find a binomial probability. So this over here is probability. This is a combination of n things x at a time. Okay, and hopefully by now you've figured out that your calculator will do combinations for you.
Yes.
Okay, if you haven't figured that out, it's in the math menu under the probability section. And then this is p to the x times q to the n minus x. And below this, I'm going to define all those things, okay? Because we don't know what n is, we don't know what x is, we don't know what the lowercase p is, we don't know what the lowercase q is. So we're going to define those below, okay? So here are the things that you need in order to use this formula. And they're related to the things that we find that makes it a binomial experiment. First off, x is the number of successes, whatever that is, whatever the problem's asking for. X is just the number of successes. N is the number of trials. P is the probability of that success for x. And then Q is the probability of failure. Okay, so what's important there is that it's not necessarily in the qualitative sense of success and failure. Like in the last example we looked at, rolling a 5 or not rolling a 5. It would have been considered that rolling a 5 was a success and rolling anything else but a 5 was a failure. It's not like, a judgment on somebody or anything like that. It's just not what exactly we're looking for. What's important here is most of the time they're either going to give us the probability of success or the probability of failure, and you're going to have to calculate the other one. And the thing that's important is since there's only 2 outcomes, the probabilities of success and the probability of failure must add up to 1. So usually the way we look at it is that the probability of failure, Q, is 1 minus whatever you have for P. Okay. Conversely, if they give you the probability of failure, then the probability of success is 1 minus the probability of failure. They're complementary. P plus Q has to equal 1. Because those are the only 2 possible outcomes in a binomial experiment, which means the sum of their probabilities must equal 1. So just keep that in mind, and when they give you some context to a problem, we'll go through one of those today, you'll have to decide, like, which one is the probability of success, and then calculate the probability of failure, that kind of thing. It's not going to be that difficult. But you need these 4 things: the number of successes, the number of trials, the probability of success, and the probability of failure. If you have those 4 things, they can all be plugged into the formula. So I have nx, px, q, and then n minus x. So what's important here to understand is that x is the number of successes, n minus x, since this is however many trials I have, is the number of failures. Because those 2 numbers have to add up to the total number of trials. So here's a problem without context. Just working through the mechanics of the formula a little bit. Okay. So they tell us n, which means there are 9 trials. Okay, so there's 9 trials. X means the number of successes, which means how many failures are there?
Oh, 7.
7. If there's 9 trials and 2 of them are successes, then I have Q number of failures. Or 7 failures, I should say. All right. The only thing that I'm missing here, what's the thing that I'm missing? for the formula? Q. I don't have the probability of, so this is the probability of success. I don't have the probability of failure, so I have to calculate that. Okay? Well, how am I going to figure that out? Okay, so what is it? 0.58. So I have everything now. Now, before you just enter the whole thing in your calculator, let's set it up and make sure we have it set up correctly. Okay? So use your formula. We have the 4 things. Plug in what you need to and see what your setup is. And then I'll show you what it should be, and we'll compare and see if you got it right. Your setup should be. Okay? So there's 9 trials, 2 successes. I take my probability of success and raise it to that power of successes. And as we already figured out, that means there's 7 failures. And keep in mind, these 2 numbers just always have to add up to the whatever our number of trials are. So if I have 2 successes, I have to have 7 failures because there's only 9 trials. Okay? Now, you could enter this whole thing in your calculator just like that and spit out an answer. Okay? That's fine. And I'm okay with that. I need this, though. Okay? So when we talk about showing work for problems like this is what I need. Now, I'm going to calculate each of these kind of individually. You don't have to. You can put it all in at once. And what you end up with is this. And I obviously went to a bunch of more decimal places just to be safe. Okay, and when I multiply that out, you should get 0.14. So whatever this situation is, okay, if I only want to figure out the probability of 2 successes, and my probability of success is basically 42%, out of 9 trials, the probability that 2 of them will be successes is 14%. Okay, so that's it without context. Let's look at one with context. How many had this, by the way? Okay, questions on it before we move on to the context problem. And I think that's the last thing we need to cover. Let me double check though. Okay. So problem with context, then we'll get into the mean and variance and standard deviation. Okay, so this is on page 272 in your book. If you would rather take a picture, screenshot it from your book. If you'd rather take a picture of the screen, you can do that too. And then we'll talk through this and figure out the answer. What we have to do here, we have to identify N, X, P, and Q. Okay, and once we do that, we can just plug it in the formula, assuming it's binomial. So let's decide if it's binomial first. Okay, 2 possible outcomes. What are they?
Gone to the doctor or not gone?
Either you went to the doctor or you didn't. So there's 2. Fixed number of trials. How many people are selected? 10. It's already set. Does one person going to the doctor impact somebody else going to the doctor? No. Okay. So I think we're good. Probability is good. All right. So we need to identify all our parts. So this is how I like to start. Identify my N, X, P, and Q. And then once I have those, I can just plug them into the formula. Okay. So how many trials do we have? 10. Number of successes. People, what is a success for this problem? They went to the doctor. How many of those do we have? 3. Okay. So we have 10 trials. 3 people are going to go to the doctor. What is the probability of success? What's the probability that somebody goes to the doctor? 1 out of 5. So 1/5. Okay. Therefore, what's the probability that somebody doesn't go to the doctor? 4/5. Okay, so I have my parts. Find it. Do it. Find the probability of 3 people going to the doctor. Go. That's what your initial setup should be. What's important, again, is if you know how many successes you have, and you know how many trials you have, then you also know how many failures you have, which means, in this case, 7 people didn't go to the doctor. And you can plug that all in your calculator and figure the answer out if you want. And notice I put the 3 in here. This is the probability of 3 people going to the doctor. And so in this case, we should have got 20%. That's interesting. How many had that? Good. Okay. Questions about that part so far? because we're going to go into the mean and the variance and standard deviation next. Okay, so just make sure you identify those 4 things. Make sure it's a binomial experiment first, and kind of go from there. So the next part, mean, variance, standard deviation from a binomial distribution. Okay, you should write this down. I realize that I'm going to put a picture up there, but I think it's better to write it down. And the mean is not hard to do because we've identified the parts that we need to find anyway. Same with the variance. It's just another little formula that you have to know. The relationship between the variance and the standard deviation is still the same. We're going to find the variance first, then we're going to take the square root of that to find the standard deviation. Okay? So here they are. Alright, so the mean, mu, is n times p. So the number of trials times the probability of success. The variance is n times p times q. The number of trials times the probability of success times the probability of failure. And the standard deviation is the square root of that. So mean NP, variance NPQ, standard deviation, square root of the variance. So again, this is not a U, this is a Greek letter mu, stands for the mean. This is not an O, this is a sigma. Sigma squared is the variance, sigma is the standard deviation. Okay. So here is a problem that we're going to look at, page 275 in your book. A die is rolled 360 times. Find the mean, variance, standard deviation of the number of 4s. So we have 2 outcomes, 4s or not 4s. And we know how many times it's going to get rolled. So there's a fixed number of trials, which is what? 360. So I have n. Okay. In mean, standard deviation, and variance, we don't need to know how many successes there were. That's the only difference. Okay, for mean and standard deviation and variance, we need the number of trials, we need the probability of success, and we need the probability of failure. We don't need to know how many successes there were. So I don't need to know x for mean and variance and standard deviation. I just need n, p, and q. What is n? 360. We have 360 trials. What is the probability of success? P. 1/6. We're rolling 4s. Okay, and there's only 1 out of 6 possibility. So what's the probability of failure then? 5/6, right? Because there's 5 other possibilities besides a 4. So those are my n, p, q. Plug them into the formulas and find the mean, the variance, and the standard deviation. Go. So, for my mean. Okay, so I made my little list. Mean, variance, standard deviation. So mean is just n times p, so 360 times 1/6, which is what? Okay, how many had that right? Very good. So then, for the variance, all I really have to do is take the mean times q. Right, because I just did NP already, but you can write it all out, it's fine. 360 times 1/6 times 5/6. So I'm really just doing 5/6 times this, because this is n times p, right? So if I list it all out, 60 times 5/6 is 50. Good. So then I just have to take the square root of 50 to come up with the standard deviation, which should be, I mean, it's 7.0 or something like that, right? Because it's pretty close to 49. 7.07 or 7.1, whatever. How many had that? Okay. That's it. That's 5-3.